last real lecture of the quarter, and Friday it's gonna be our review section. I did some update on our announcement. So since our last lecture, we didn't end up go as far as I want. So we will only cover chapter 6 for this quarter. So today I'll finish up on chapter 6. So you will still see lecture 2021, which are on phase diagram, and chapter 7, phase rule, phase diagram, Clapeyron equation. So those are there for your reference, but I won't test you on those material this quarter since we did not end up covering chapter 7. Now that being said, in your future career, people will still expect you to know how to read the phase diagram. So I also uploaded my lecture note there. It's also in the textbook, and it's for your reference. Hopefully you will have some time to read it yourself. Okay, and again, everything else stays the same. I want to say one more thing regarding our preparation for the final exam. So when making the final exam, I have the tendency of recycle problems that lots of people didn't do well in previous midterm exams. So I highly recommend you go back to our previous midterm 1 and midterm 2, especially in problems that you missed, right? So look at those problems again and make sure you understand what you did wrong. If that same problem appears again in the final exam with a different version, can you do it right in the final exam? All right, so that's more like a tutorial to prepare you for the final exam. In addition, I have also posted the answer key to the my last quarter's final exam. Note that in the last quarter, I went through chapter 7, right? So there are problems related to phase diagram and Clapeyron equation that's not applicable to you, right? So for those questions, I crossed out in the final answer key. And also, I recognize that you also have lots of different things going on, and my Tuesday office hour may not be the best time for you. So I'll host one extra office hour this Friday. So it's gonna be the same time, 1 to 3 p.m. in my Young Hall office. All right, so that's this Friday. If you wanna stop by, chat about anything, I'll be there. But if nobody shows up until 2, I'll just leave, right? So just so you know. Okay, and also I posted a quick note there, if people just don't show up, I may go to my research office, but I'm still around, right? So send me an email and tell me hey, I'm in front of your office. I'll head down in a few minutes. All right, any administrative questions before we move on to today's lecture? Okay, I also printed out the blank copy of our today's lecture in case you want to have it, but if you already did, it's fine. So as a quick review, in our last lecture, we went over ideal gas equilibrium calculations, right? So for entire chapter 6, we started by reviewing what is chemical equilibrium, what is the relationship between Gibbs free energy and the ideal gas reaction equilibrium. We defined equilibrium constant, went over how does that equilibrium constant change with respect to temperature, or aka the Bentov equation. So in our last lecture, we went over the general procedure to show that how to do ideal gas equilibrium calculations, right? So the first step is looking at what are the things we know, right? So these are the equations we know. Delta G naught equals to negative RT ln K. We have definition of our equilibrium constant for ideal gas reactions. And then we also say hey, you can calculate the delta G of the reaction from the thermodynamics table. And there are several steps we use to calculate equilibrium composition for an ideal gas reaction. So we went over an example together to look at how to calculate the equilibrium composition at 298 Kelvin. But there's one more step you can potentially take, and I think you have that in your discussion worksheet. For example, if the question is asking you to find the delta G or the equilibrium constant at a temperature different from 298 Kelvin, what should we do? So the first step, you can get the delta G or the Gibbs free energy of the reaction at 298 Kelvin. Right, so that's something you can get. So the delta G of the reaction at 298 Kelvin. We can translate that using delta G equals to negative RT ln Kp to get the ln Kp, or the equilibrium constant, at 298 Kelvin. All right, but if the question is asking you to find the equilibrium constant at a different temperature, right? If that temperature difference is small or big, you can use the Van 't Hoff equation in different way, right? So let's assume our delta T is like, say, 100 Kelvin, which is small. So if our delta T is 100 Kelvin, right? So for example, we're trying to find the Kp naught of at say 398 Kelvin. So how do we do that? So we started from the Kp naught at 298 Kelvin. We searched the table to find the delta H naught of 298 Kelvin. And using the assumption that when delta T is small, my delta H naught will be a constant. All right, and use that constant in our Van 't Hoff equation, we can calculate how does my ln Kp change with respect to temperature. And then, using the Van 't Hoff equation, we'll be able to solve my Kp naught at 398 Kelvin, and then use that to go back to solve my delta G naught at 398 Kelvin. Right, so that's the logic behind how to solve equilibrium constant or Gibbs free energy of the reaction at a different temperature. Alternatively, if my delta T is bigger than 100 Kelvin to like 2000 Kelvin, so that's one example question you see in our practice final exam, then we need to give you an expression of delta H naught as a function of temperature, or the isobaric heat capacity of the reaction as a function of temperature. Right? So there are two different ways we can solve it. But the fundamental idea here is you start from the standard 298 Kelvin delta G and equilibrium constant, using the Van 't Hoff equation to address how does my equilibrium constant or delta G change with respect to temperature, and then go back to use that new equilibrium constant or delta G we solved for your specific reaction of interest. All right, so that's a quick clarification in what you should be doing, like how to set up that calculation when we need it. Okay, and in our last lecture, we went over this example here following the 6th step, right? So the first step is to solve for using the tabulated data, solve the delta G of the reaction. Second step, find the equilibrium constant. If it's at 298 Kelvin, we can directly use it. If it's not, we need to use the Van 't Hoff equation. And then express equilibrium Moore numbers, and then calculate the partial pressure, and use the equilibrium constant definition to solve for the extent of reaction. And by solving that quadratic equation, you can express a number of Moore at equilibrium for each composite, for each species. All right, so the example question we did together is this example, which is the decomposition of N2O4 into 2NO2. And basically, we demonstrated that by using the thermodynamic table, we can solve what is the equilibrium composition for a given reaction by only knowing the initial number of Moore of your reactant and product. All right, so this part is something we did in our last lecture. And let's do one more example question together, because instead of getting a numeric answer, another thing we can do is to write the equilibrium composition using the equilibrium constant. So if we read this question together, we're giving you that suppose a gas phase isomerization reaction between 3 different chemical species, random ones, A, B, and C. So there are three sets of equilibrium existing between these three chemical species, right? A and B, B and C, A and C. And we tell you these ideal gas isomerization will reach equilibrium at certain temperature T, and ask you to express equilibrium mole fractions of A, B, and C in terms of equilibrium constant. So this is one of those questions that you will not get a numeric answer. It is important to know how to set up this question. Right? So the first thing first I like to do is write out what the question is asking about. It says express the equilibrium mole fractions of A, B, and C. So we're looking for chi A, chi B, and chi C. And we want to express my chi A, chi B, and chi C with equilibrium constant. So we have three equilibrium constant. So the equilibrium constant between A and B, equilibrium constant between B and C, and equilibrium constant between A and C. All right. And what else do we know? So this is the first step, is to read the question and write out what the question is asking about. What else do we know? So first thing, write out what the question is asking about. Second thing, write out what do we know about these properties that the question is asking about. Right. So for example, the mole fraction. What do we know about mole fraction? So for example, if we use A as an example, that equals to partial pressure of A over our total pressure P. All right, so first step, write out what the question is asking. Second step, using our knowledge to write out what do we know about these properties that the question is asking about. What else do we know? We also have the definition of our equilibrium constant. Right, so using our A, B equilibrium constant as an example, that equals to my PB over P to the stoichiometric coefficient of B over PA over P to the stoichiometric coefficient of A. And in here, we only have 1 and 1, right? So that you can effectively write to be PB over PA, because this one is 1. This one is also 1. And my standard pressure will cancel out. And my PB over PA is effectively the same as my chi A over chi B. Wait, chi B over chi A, sorry. All right, so this part is, well, first we write out what do we want. Secondly is, do we have anything we know by looking at the definition of the mole fraction, by looking at the definition of my equilibrium constant? And now obviously there is a relationship between my equilibrium constant and the mole fractions. So now what's next, right? So for example, in this case, what do we have here? Using this equation, we can find out that you can write chi B equals to chi A times equilibrium constant of A to B. And you can do the same for all three of them, right? It's the same logic. You can also write my chi C A to C as my K A to C as chi C over chi A, my equilibrium constant between B to C equals to chi C over chi B. Right, so the logic is again the same. We're just using the definition of equilibrium constant of the three equilibrium here. Now from here, obviously we can translate these two equations into this format again. So what else do we have? So from here, we can write my chi C equals to chi A times K AC, and my chi C equals to chi B times K B to C. Now, what else do we know about mole fraction? We have the definition of mole fraction. We have definition of equilibrium constant. We use these two relationships to give us an expression of how to link my mole fractions using equilibrium constant. There's one more thing we know about mole fraction. At the end of the day, your mole fraction will always add up to be 1. It's a fraction, right? So naturally, the mole fraction will always add up to be 1. Or the way to say it is my chi total will equal to chi A plus chi B plus chi C. That always adds up to be 1. So in here, what else do we have? Now, if we think about chi A, that's just chi A. My chi B equals to chi A times K A B. That's where this comes from. And my chi C equals to my chi A times K A and C. Right. So taking together, we now have an expression that is chi A plus chi A times K AB plus chi A times K AC equals to 1. Right, remember what we want. We want to express chi A, the mole fraction of A, as a function of equilibrium constant. So that equals to 1 over 1 plus K AB plus K AC. Right. And from here, the expression of my chi B and chi C are pretty straightforward, because we know that chi B equals to chi A times K A to B. So that naturally equals to my K AB over 1 plus K AB plus K AC. And the same applies to the mole fraction of C. Right, so by only using the definition of mole fraction and also equilibrium constant, we can get a general expression for any kind of isomerization. Now, this equation will definitely change, right? So if you think about it, now instead of having A to B, A to C, and B to C, where the stoichiometric number is the same, what if we have like 2 in front of B and then 2 in front of B here, right? So naturally, that will change our final expression of how do we express my mole fraction with the equilibrium constant. But the logic is the same. Right? You write down the definition of equilibrium constant, write down the definition of mole fraction, knowing that mole fraction adds up to be 1. We have enough things to get our final result here. All right. So this part is basically we did 2 examples together to show that how do we use the definition of equilibrium constant to solve for equilibrium composition, right? So what is the composition of your different starting material or product at equilibrium? Okay, and the last part we want to cover for chapter 6 is shifts in ideal gas reaction equilibria. So when we say shifts in reaction equilibria, what we're saying is now imagine a system at equilibrium, nice and happy. Now we're doing things to the system, whether it's changing temperature, changing pressure, changing volume, adding inert gas, adding reactant gas, or adding product gas into the mixture. How will that action shift our equilibrium? Will it push the equilibrium backwards, forwards, or stay the same? Right. So the general logic we approach the shifts in ideal gas equilibria is to compare the reaction quotient with our equilibrium constant. So the equilibrium constant, right, remember we have our equilibrium constant defined as the sum of my partial pressure at equilibrium over P naught to the stoichiometric coefficient. In comparison, the reaction quotient is defined as partial pressure, the instantaneous partial pressure of the system. All right, so equilibrium constant is defined based on the partial pressure at equilibrium. And by comparing the dimensionality of your reaction quotient with our equilibrium constant, we can tell whether or not the reaction is forward, backwards, or at equilibrium. All right, so again, for reaction quotient, this Pi here is the instantaneous partial pressure. Of I. So whenever we have our reaction quotient smaller than Kp, we're predicting it to be a forward reaction. Equal to Kp, it's the same as at equilibrium. Larger than Kp means it's backward reaction. Yes?
So that means that the partial pressure just be the initial condition?
Well, I don't want to say initial condition because it's a little bit misleading. I want to say the partial pressure here in the reaction quotient. It's just say, hey, this is the partial pressure at this moment when we're asking the question. All right. And let's see one example together to see how that's being applied. Let's imagine we have isobaric temperature change. So isobaric temperature change, what does it mean? Isobaric means our total pressure remains the same. Only temperature is changing, so the composition is not changing, right? So my Pi equals to chi I times total pressure P. So naturally, my Pi is not changing, right? So my Pi is not changing, suggesting my reaction quotient is not changing when we are changing the temperature. However, we have the Van 't Hoff's equation, right? We're always comparing the reaction quotient with the equilibrium constant. But when we're changing the temperature, the equilibrium constant will change with respect to the temperature, right? So using the Van 't Hoff's equation, what do we have? Now, we can write, well, so there are some simplification that we did before, because if we have d ln Kp over d Kp naught, that gives me 1 over Kp naught, right? We're just taking the derivative of a ln x over x. Or the other way to put it is d ln Kp naught equals to 1 over Kp naught d Kp naught. Just using a little bit calculus to simplify this problem. Or we can rewrite my d Kp naught over dt equals to Kp naught times delta H naught over RT squared. It's okay if you don't do that, because ln Kp will always change the same way as Kp naught changes. But the take-home message here is, in this relationship, my Kp naught, R, and T, these three things are always going to be positive. Right, so how does the Kp naught change, how does my equilibrium constant change with respect to temperature depends on the sign of my delta H, or depends on whether my reaction is exothermic or endothermic. Right, so for positive delta H naught, what do we have? Right, so this one is endothermic. And an endothermic reaction, positive delta H, that means my dKp naught or my Kp naught will increase with respect to temperature. All right. Alternatively, if we have exothermic reaction, we have negative delta H naught. So my Kp naught will decrease with temperature. And how do we tell whether a reaction is endothermic or exothermic? You can refer to the appendix table to calculate the delta H of the reaction to decide whether or not the reaction absorbs or releases heat. Or we can get a more general conclusion for the isobaric temperature change. So this one is generally true. When we see an increase in temperature at constant pressure in a closed system, always shift the equilibria in the direction in which system absorbs heat from surrounding. It's longer, but it's basically restating what we just went over. All right, so this one is an example to see like how do we approach the problem. You first read it as isobaric temperature change. So you want to think about it. Is my reaction quotient changing, or is my equilibrium constant changing? Right, equilibrium constant is only a function of temperature. So my equilibrium constant is changing. So how does my reaction shift? Right, so if my equilibrium constant is increasing, my reaction quotient remains the same. Then for an endothermic reaction, when my temperature increases, equilibrium constant increase with it, then my reaction quotient is smaller than equilibrium constant. We predict a forward reaction. Right, so that's the logic behind this kind of question. And what about a different scenario, right? So these looks a little bit tedious, but the nature behind all these arguments are the same. Like for example, let's look at a different scenario. We have isothermal pressure change. Right, so what does that mean when we say isothermal pressure change? So isothermal tells me my temperature is not changing, or the other way to put it is that my isothermal pressure change is my P in my initial state will remain the same in all cases. Then what we have, so if we look at the partial pressure of my species A and B, so the partial pressure of my species A is a more fraction of A times the total pressure P. In the initial state, my PB equals to chi B P. Right, so initial state, we're saying this one is the P equilibrium. So we can write it out to say like, hey, what is our equilibrium constant? So my equilibrium constant equals to the product of my partial pressure over P naught to the stoichiometric coefficient, which in this case, negative A and positive B. All right, so that's the expression for our equilibrium constant. Now, is my equilibrium constant changing when we're changing the total pressure at isothermal condition? My equilibrium constant is a function of temperature only, so the equilibrium constant itself is not changing. But when we are changing the pressure, the reaction quotient will change. right? So remember the reaction quotient is defined as, well, so this one is basically telling you my Kp naught is not changing for isothermal processes. And what about my reaction quotient? Now my reaction quotient is equal to the product of my partial pressure to the stoichiometric coefficient. So we're looking at chi A. Now imagine we're instantaneously changing my pressure into 3 times, so 3p equilibrium. So chi A times 3p minus A, chi B times 3p to the power of b. All right, so what are we comparing? What are we comparing is which one is bigger on the top one and on the bottom one. Or the question we're trying to answer here is when my pressure is increased like triple times, right? So the nature of how does that reaction equilibrium change depends on the nature of the reaction. What is the number of mole? What is the stoichiometric coefficient A and B? Right, so if my A is smaller than B, I will have my QP larger than KP, meaning a backward reaction, and vice versa. All right, so the nature here is when we're looking at an isothermal pressure change. Isothermal tells us Kp is not changing, equilibrium constant is not changing for isothermal processes. But we can write out the expression of Qp using the instantaneous changed partial pressure and compare that Qp with the equilibrium constant. Or in general, we can write it out to say like an increase of pressure at constant temperature in a closed system will always shift equilibrium in the direction to which the system volume decrease. What about addition of gases? Right, so in this case, let's look at an example here. We have isochloric addition of inert gas. So it are telling you the temperature is not changing and volume is not changing. This is isochloric. So we're adding inert gas into there. So what do we know? First of all, we know that constant temperature. Or telling us my Kp naught is not changing. Right, because temperature is not changing, my equilibrium constant remains the same. And what about my reaction quotient? Now my reaction quotient, again, is defined as the product of my partial pressure to the stoichiometric coefficient. So what is my PI here? So my PI here, or the partial pressure of my specific species, we have PV equals nRT for ideal gases. So if my volume is not changing, my PI will always equal to NI RT over P. Over V, sorry. Right, so temperature is not changing, volume is not changing, R is a constant. We're adding an inert gas. So the number of mole of my reactant or the product of my species I, Ni is also not changing. So my partial pressure is not changing if the volume is kept constant. Right. We're increasing the total pressure, and at the same time, we're changing the mole fraction by adding the inert gas. So this will mean we have no effect on the position of equilibrium if we're adding the inert gas at constant temperature and volume. We'll see an example of like why it's different if we're adding the inert gas at constant temperature and pressure. All right, so to answer these kind of questions, I highly recommend you don't try to remember what our conclusion is. like actually write down what is going on, like how do we get to the conclusion? Because it's very easy to miss the condition if you're just trying to memorize everything. Okay, next up, addition of reactant gas. Now, when I say reactant gas, it can also be a product, right? So how does it shift our equilibrium if we're adding a substance A to the reaction mixture? So there are two different types of addition of reactant gas. You can add it at constant temperature and volume, or you can add it at constant temperature and pressure. So in here, we're trying to revisit the Le Chatelier principle, right? So you probably learned it in either high school or Gen Chem, the Le Chatelier principle, adding reactant gas, you're pushing the reaction forward, adding product, you're pushing the reaction backwards. But now we're trying to demonstrate like it's not always true. So the Le Chatelier principle, we need to rephrase it in the PChem setup in order to make it more accurate. Now, if we look at our constant temperature and volume scenario, first of all, constant temperature tells me my Kp is not changing. What else do we know? We have our total volume, right? So when volume is kept the same, I have my Pi equals to Ni times RT over V. That's a derivation we did before. Now, in this example, imagine we're adding substance A, or my reactant A, to the mixture. So what we can write? We can write my Qp, my reaction quotient, after addition of A to be Pc squared Pd, Pa minus 1, and Pb minus 1. Right, so in here, there are several things that's not changing, right? So my C, D, and B, these will stay the same. And my PA will increase. Because we're adding A to the mixture. Right, so what are we having? We're having my QP decrease with PA, right? So we have a -1 of the stoichiometric coefficient here, and we're predicting my QP to be smaller than KP, so a forward reaction. So far so good, right? Looks like our Le Chatelier principle is working. But now let's look at our constant TP scenario and see why we say you want to be very careful when using the Le Chatelier principle. So constant TP, again, constant temperature, so my Kp naught is not changing. And what is my Pi? Now my total volume is changing. We're keeping it at constant pressure, so we can only use my Chi times P to solve for the partial pressure. Now we have a question, because since my Chi also depends on what reaction we're talking about and how much did we add to the reaction mixture. So the movement of the equilibrium largely depends on the nature of the reaction. And let's see one example question here to see like why you shouldn't be using the Le Chatelier principle by just looking at the number of mole of substance added to it. So use our ammonia formation reaction again. Well, obviously assuming everything is ideal gas. Right, so we say that equilibrium is reached at certain temperature and pressure. So on the left-hand side, just to simplify our work, let's use the mole fraction version of the equilibrium constant and the reaction quotient. It's the same idea, just like replacing that partial pressure with a mole fraction here. Since our pressure is kept constant, they're effectively the same as we did with the partial pressure. All right. So what do we have? Now thinking about the initial condition. At equilibrium. right? So that's at our equilibrium condition. Let's say we give you the number of mole of my NH3 at equilibrium is 1.0. Number of mole of your N2 at equilibrium is 3.0. Number of mole of H2 at equilibrium is 1.0 more. So we can calculate our mole fraction of my species at equilibrium. Right, so this is 1/5. This one, and 2 at equilibrium, that's 3/5. And H2 at equilibrium is 1/5 again. Right, so by looking at our initial condition at equilibrium, we can calculate my K at equilibrium equals to, so let's see my point, oh, this one is 0.2, 0.6, 0.2. So 0.2 square over 0.6 times 0.2 third. Right, so we do that calculation, you get 8.333. That's our equilibrium constant. Now imagine we're adding our reactant to this mixture. So the reactant we're adding here is 0.1 more of N2. So what does that mean? It means my number of mole, the instantaneous number of mole after addition of N2, my NH3 number of mole remain the same. My N2 now becomes 3.10. My number of mole of H2 at the moment when we add the N2 to the mixture will remain the same, which is 1.00. So we can calculate the instantaneous mole fraction of each species. For NH3 now is 1/5.1, and that's about 0.196. That for N2 is 3.1/5.1. That's about 0.608. And that's for H2 is 1/5.1. It's about 0.196. All right, so what's our reaction quotient? Right, so our reaction quotient, that's equals to my 0.196, that's my product, which is here, to the square, 0.608 times 0.196 to the cube. And we estimate that to be 8.392. What does that mean? So that tells us in the reaction mixture of my ammonia formation reaction, adding my reactant will actually make my reaction quotient to be larger than my equilibrium constant. All right, so what does it mean? So my Qx is larger than my Kx, and that tells me we have a backward reaction. So it doesn't fit your simple Le Chatelier principle. And why is it? If we look at the number of mole, we can tell that the number of mole of my N2 is actually increased even if we added that my reactant. Or the other way to put it is when we're saying the Le Chatelier principle, we want to rephrase it in a way that we're only using the intensive variables. All right, so the number of mole of reactant or product, that's not a very good way to use the Le Chatelier principle. You want to replace that with intensive properties like mole fraction. So in this example, if we rephrase the Le Chatelier principle, we want to say in a system at equilibrium, a change in one of the intensive variables, that determines the equilibrium will shift the equilibrium in the direction contracting the change of that intensive variable. And that intensive variable we're saying here, including like temperature, pressure, and mole fraction. Right. And then we have about 5 minutes left. So I'm gonna, well, we only have example questions together and we can do that together on Friday. But before we do that, I'm just gonna use this 6.48 as an example to see like how to approach this kind of questions and asking for shifts of equilibrium constant. Right, so for a reaction that's given, it's asking you to state whether or not equilibrium shifts right, left, or not changing. And you can use appendix data. So to answer this kind of question, you want to first write out the definition of my equilibrium constant and reaction quotient. So first of all, write out what we know, right? So what do we know? We have our reaction quotient equals to the product of my partial pressure to the stoichiometric coefficient. Right, so my partial pressure equals to Ni RT over V for constant volume scenarios, and my partial pressure equals to chi I times pressure for constant pressure. So depending on if we're talking about constant volume or constant pressure, you want to use different equations to solve for that partial pressure. That's one thing. Secondly, equilibrium constant. So know that our equilibrium constant is only a function of temperature. So whenever you have isothermal, we're saying my Kp naught is not changing. All right. And at the end, we have our relationship. So if my Qp naught is smaller than Kp naught, we're expecting forward reaction. And if my Qp naught is larger than Kp naught, we're expecting backward reaction. And in here, when we're talking about Kp naught changes with respect to temperature, we have our d Kp naught over dt equals to Kp naught delta H naught over RT squared. Right, so how does the equilibrium constant change with respect to temperature depends on the nature of the reaction, whether the reaction is exothermic or endothermic. So we'll pick it up from here since it's just practice. We already covered everything I want you to know. It's just practice problem together. So I'll do this practice together on Friday. In addition, on Friday, I'll do an overall review in what we covered this quarter. And again, what is thermodynamics, right? So what you have learned, like leave out all the math and all the equations. Why do we need thermodynamics? So hopefully I'll give you an overview in everything we covered. And that's all from me this quarter, and I'll see you on Friday.